Hello, and welcome to the Intelligent Transportation Systems Masterclass, sponsored by the Florida Department of Transportation and presented by AtkinsRealis. This is intended to be a multi-part educational resource in which we will discuss the Intelligent Transportation Systems basics. Today we will cover Fiber Optics 101, Basics in Cabling. My name is Nathan.Mozeleski, and I'm excited to lead you through this fiber optic journey. In today's presentation, we will have three primary objectives. 1. Understand how fiber optic technology works. 2. We want to gain a perspective of why the department employs fiber optic communications. And 3. We want to learn what fiber optic communication is used in a typical construction project installation. Whenever you see this symbol, this will denote that subject matter is being pulled directly from a Florida Department of Transportation reference. This might include the FDOT Design Manual, or FDM, standard plans, or standard specifications. Let's start today with some background knowledge. Before we jump into fiber optic communications, let's take a refresher on some of the overarching concepts for all digital communications. Number 1, what are the smallest units of digital communications? If you answered bits or binary digits, you are correct. Binary digits, or bits, create the smallest form of digital communications. Leading into our second question, at the most basic level, what is transmitted and received between devices in digital communications? Look to the image to the right, you'll see a clear illustration of the difference between bit, byte, and word. A bit is an instance of a 0 or a 1 in digital communications, which makes sense if you think about the definition of binary and digits. Digits are simply numbers. Binary is the selection of one of two finite options. Examples might include yes, no, or on and off. A byte is the collection of 8 bits together. This represents the primary unit that we will consider in communications. So every time that you think of 8 bits, that is 1 byte. And word is really the collection of more than 2 bytes. So as you are spelling out things like onomatopoeia, that is a collection of bytes which can then be broken down further into bits. So these are terms and concepts that'll come up throughout digital communications, including fiber optics. Taking what we know about digital communication in bits, we can apply that directly to fiber optics. Fiber optics is defined as a class of technology that utilizes glass threads to transmit pulses of light carrying information at high speeds from one point to another. Remember, bits are ones and zeros, which is a binary digit. When we talk about light and binary, we can talk on and off. So every time the light is on, that can be considered a 1, and every time the light is off, that can be considered your 0. Okay, so how does it all work? What happens is data is provided to the source. This is the transmitter, which is outfitted with an LED or laser ready to send pulses of light down the fiber optic strand. The transmitter will receive that data and encode it into a sequence of bits. Remember, those are your ones and zeros, using that light source, i.e. the LED or laser, to transmit that data. The transmitter will use that LED or laser source to then send light pulses down the fiber optic pathway from the source to the destination. The receiver has a photocell or light detector that is able to receive the individual pulses of light. The receiver then ingests that series of bits, those light pulses, zeros and ones, and converts it into data that can then be used by other networking equipment. The light pulses that are sent from the source and received by the destination travel down each individual fiber optic strand by a process called total internal reflection. What this really means is that fiber optics allow light to travel through the core of the fiber, which is surrounded by a reflective layer called cladding. This is really similar to a very thin tinfoil. Light bounces along the fiber optic strand from the source to the destination, bouncing between the cladding, as you can see here in this image. This is the process known as internal reflection. In order to ensure that the data gets from point A to point B, the fiber optic pathway needs to be continuous from one point to another. As light continues to bounce between the levels of the cladding, we need to ensure that we don't have breaks or damages in which light can escape. Remember, we're talking about a sequence of ones and zeros. And if there are zeros or ones lost in that sequence, the data that is sent and the data that received will be different. And therefore, it's really important that we have good, clean lines of fiber optic communication that allow light to traverse the entire length without any light loss. The implementation of fiber optic communications enables high-speed data exchanges and roadside applications. And with the number of benefits provided by fiber optics, it makes it a really attractive choice. Fiber optics provides higher speeds and longer distance. Fiber can travel approximately 2/3 the speed of light, which is approximately 100 times faster than copper communications. And that data can be routed many miles from point A to point B, which is a major upgrade over traditional copper communications. Fiber optics also provides greater bandwidth, which means using one cable, we can deliver 1,000 times more throughput of data versus traditional copper. Fiber optics also provides better reliability. Fiber is dielectric, which means it does not transmit electrical current. This is safer for both installers and maintenance professionals, but it also makes it resistant to EMI, or electromagnetic interference, and changes in temperature that can degrade or disrupt signal. And finally, fiber optics is more secure. The physics of optical light traversing from point A to point B make it really difficult to intercept by anyone who may be ill-intentioned. There is a con with fiber optic communications though, and that is the cost. Versus traditional copper, fiber optic installations and the equipment associated with it can oftentimes be much more expensive. Okay, so now that we understand a high idea of how fiber optic communications works and some of the benefits, let's dive into the components of a fiber optic cable. In order to make this a little bit more simple, I'd like you guys to think about Russian nesting dolls, as we will continue to build upwards. What you see on the screen here is the profile view and a cross-section of a typical 144 count single mode fiber. But we're going to start at the smallest level with the individual fiber itself. When we think about the scale of fiber optic communications, I want you to remember that each individual fiber is roughly the diameter of a human hair. This means when we're dealing with the installation or maintenance of fiber, we're dealing with really sensitive, small items. Imagine trying to take 2 hairs from your head and putting them end to end to allow light to pass through. That's roughly the size and the scale that we're dealing with. Each fiber is comprised of 3 primary parts. You've got the core, the cladding, and the coating. The core is the central cylinder made primarily of glass or plastic that guides light from end to end. You can think of this as the pathway. We talked a little bit about the cladding earlier, but this is the reflective layer that is wrapped entirely around the core that helps us confine the light or allows the light to bounce between the various layers of cladding from one end to another. The coating is really just our protective outer layer. The 3 elements combined make up each individual fiber. It's really important to understand that there are 2 types of fiber optics: single mode and multi-mode. Within the realm of intelligent transportation systems, we use predominantly single mode communications, which includes a smaller core, around 10 micrometers, transmitting a single signal using laser diodes. So it's really important to remember two things here. Each single mode fiber uses laser diodes, traditionally at about 1310 and 1550 nanometers, and that laser produces a single predictable wavelength. This is known as coherent. So when you think single mode, think one. The pros to single mode are that it has a greater transmission distance, up to 100 kilometers. So that means we can have runs of fiber optic, if they're single mode, stretch up to 100 kilometers. And it also provides a high bandwidth of communications. The con with single mode is it can tend to be more expensive. Conversely, multi-mode fiber is, as you could expect, a larger fiber that allows us to send multiple simultaneous communications. Multimode fibers typically have a core ranging between 50 or 62.5 micrometers in diameter. And instead of lasers, multimode uses LED sources. So this incoherent wavelength allows us to send multiple signals using the same fiber, which is completely different than the single mode, which only allows for one transmission of signal. Some of the pros with multimode are it's easier to install and it has lower cost of the networking equipment. LEDs tend to be cheaper than laser sources. One of the major cons with multimode, though, is it has a limited distance as opposed to single mode fiber optics. In short, multimode cannot send the multiple simultaneous wavelengths as far as single mode can send a single point-to-point laser-driven source. When we think about fiber optic cables, it's a collection of those individual fibers. So again, back to our Russian nesting dolls, we're going to get to the next level bigger and talk about buffer tubes. Buffer tubes are a collection of two or more fibers that are organized together for ease of maintenance and installation. Buffer tubes are limited to a maximum of 12 individual fibers each. This is a really important concept that I'd like you to remember. Fibers are constructed with unique colors to help distinguish each individual fiber within the buffer tube. This is an industry standard from the TIA 598D standard. What that means is the first fiber in every buffer tube will always be colored blue, the second orange, the third green, the fourth brown, and so forth. This pattern will repeat itself for each individual buffer tube. So if you have 144 count fiber optic cable, you will have 12 buffer tubes with each buffer tube containing 12 individual fibers of this color scheme. So it's really helpful if you can remember blue, orange, green, brown, slate white, red, black, yellow, violet, rose, aqua. That pattern will repeat again and again and again when you're dealing with fiber optic communications. Within cables, we typically have more than one buffer tube. So again, we're getting bigger and bigger. There are 12 fibers within a buffer tube, and this 144 count single mode fiber has 12 buffer tubes within that cabling. This collection of buffer tubes is now organized into our fiber optic cable. Now, again, I mentioned that the color scheme is extremely important to remember. And while it does apply to the individual fibers within a buffer tube, it also applies to the buffer tubes themselves. Each buffer tube is constructed with a unique color following the same color schema as the fibers. So this means if you had 12 buffer tubes within a cable, that first buffer tube would be blue. The second buffer tube would be orange, the third green, and so on and so forth. As such, cables are typically constructed in counts of 12. This means you're unlikely to find a cable with 35 or 47, and typically you'll find 12, 24, 36, 48, 72, 144 count fibers. And this is a direct result of the common TIA 598D color schema with repeating multiples of 12. Now, let's just do a quick little brain exercise. If I asked you what is the color of the 61st fiber, how would you go about figuring that out? We would first start by thinking about our multiples of 12. The 61st fiber means that we would have 5 repeating iterations of the complete buffer tube. Blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, aqua. We would have 5 buffer tubes completely filled of that schema. That would get us to 60. Then the 61st would be the first fiber in the remaining buffer tube, or the blue fiber. So that means the 61st fiber would be the blue fiber in the 6th buffer tube. So if I asked, what happens when cables exceed 144 individual fibers? How would we have the buffer tubes within cables colored? Obviously, at this point, we've exhausted all 12 of our colors in both the fibers and the buffer tubes. So TIA 598D defines a striping method. So as you can see here in this table, buffer tubes that exceed 144 will get black stripes or yellow stripe if you're the black buffer. And then if we have a pattern repeating beyond that, we will go to red stripes, green stripes, so on and so forth. In addition to the individual fibers and buffer tubes, a fiber optic cable is made up of numerous components. On the left, you'll see a great cross-sectional illustration demonstrating each of the individual components and where they reside in the cable. At the very center is the central strength member. This is a core for the cable that provides structural rigidity, and it's used as a primary element for pooling or installation. We wouldn't want to attach equipment to individual fibers, which are fragile and very keen to break. So we'd rather have all of our pooling, our tension, our force applied to this central strength member, which is typically made of some sort of solid plastic core. Within the cable, we also have our water blocking material. This is located between or within the sheath, but in between the buffer tubes, and prevents moisture from collecting inside of the cable, which will ultimately lead to rot. So this is sort of a resiliency measure. The ripcord is a sturdy yarn embedded within the jacket that allows you to access the interior of the cable quickly. Effectively, you grab the ripcord and yank it, and it'll open up the jacket, revealing what's inside. Strength yarns are twisting aramid threads providing additional strength to supplement the central core member. And the outer sheath, or what we commonly refer to as the jacket, is simply the outermost protective layer of the cable, and it allows the cable to be stamped or printed upon key information. For example, the manufacturer, the count of the fiber, when it was installed, and the individual footage of the cable. While many of the components used in fiber optic cables are the same, there are a variety of different form factors or types of cables and how they are built. The specific cabling type, common type of cable that we see deployed for fiber optic installations on DOT or other public municipal jobs is the loose tube type cable. This is specifically engineered for harsh environments and outdoor applications. This is the cable that we were looking at the cross section on the last slide. Multiple buffer tubes centered around a central strength member, and some will include water resistant gel. Now, before you subscribe to the water resistant gel, check the specifications and preferences of the local maintaining agency, as some agencies are moving away from the inclusion of water resistant gel within cables due to the maintenance nightmare that it has sometimes created. Other types of fiber optic cable include tight buffer, This is best suited for indoor applications and really includes 2 layers of coating and is typically gel-free. Due to the fact that it's predominantly engineered for indoor applications, we do not use this for department projects. Ribbon fiber optic cables are developed for outdoor applications and provide the highest density of fibers per diameter of fiber optic cabling. This means that even the smallest cable will have a high density of fibers for individual connections. What happens is fibers are constructed horizontally, 12 fibers per row, allowing for splicing to be done 12 fibers at a time. You'll often see this type of cable in third-party communication providers like AT&T or Comcast or Spectrum. We don't typically use this for DOT type jobs. Armored fiber optic cables are made for outdoor installations, typically direct burial installations, and include a metallic protective layer between the buffer tubes and the outer jacket that is resistant to heavy crush loads or damaging nuisance wildlife. For example, rats, rabbits, or squirrels. One thing to be considered with armored cables is it needs to be grounded, as it does now have the ability to carry an electrical signal through. And the last type of fiber optic cable is aerial cable. These are specially manufactured cables that include a steel messenger wire within the jacket to support the dead load of the cable for overhead spans. So as this cable is installed from pole to pole, that messenger wire will be responsible for carrying the dead load and the tensile forces and not the central strength member. Regardless of the fiber optic cable type used, one thing is common with all fiber optic cable, and that is it's developed using glass, which means that we've got really fragile fibers within these cables, and we need to be cognizant of that. The concept of minimum bending radius is a critical consideration for fiber optic cables. And what this means is that you cannot bend a cable beyond this point before you start seeing the individual fibers, the glass, start to snap and damage or be broken. There are 2 types of damages that can occur from bending radius violations, and that is micro bend down here on the left and macro bend over here on the right. Both microbend and macrobend result in either loss or incomplete transmission of data due to loss of light throughout the fiber optic cable pathway. During design and construction, it's really important that we make sure that the minimum bending radius is reviewed and considered to ensure that we can provide end-to-end communication transmission from one end to another without light loss due to micro or macro bending. Typical minimum bending radius requirements may vary based on the situation, but below we have included some of the industry standards. Minimum bending radius of a cable during loaded conditions or during installation when we've got a tensile force pulling it is 20 times the diameter of the cable. This means if you had a 1-inch diameter cable, the minimum bending radius could not exceed 20 inches. Similarly, the minimum unloaded bending radius, or post-installation, is 10 times the diameter of the cable. So if you had that same 1-inch cable, once it was installed, you could not bend that cable smaller than 10 inches. And finally, when you're placing fiber optic cable in a box or a splice vault, the best practice is to not bend that cable less than 14 times the diameter of the cable. And this is for long-term storage. The figure on the right is a really clear example of how you can calculate the minimum bending radius for your own individual situation. Taking the outside diameter of the cable and then multiplying that by the multiplier based upon your situation. Let's now take a look at what the Florida Department of Transportation references say about fiber optic communications. The intent of looking at this section is to help engineers, designers, and project managers identify what requirements the department has set forth for the fiber optic communications. And really, we're going to be trying to bridge a gap between what resources say and what we've talked about earlier in the presentation. Remember, when you see this symbol on the right-hand side, this is language being pulled directly from an FDOT resource. For example, this one is from the Florida Department of Transportation Design Manual, or FDM, section 233.5.1. Within the FDM, it says that we should design all of the ITS applications for single mode fiber, as you can see that highlighted here in yellow. The other thing that I'd like to point out is that it identifies that 144 single mode fibers as a minimum should be used for new fiber optic backbones. Looking now at the standard specifications, section 633, you can see here, highlighted at the top, where it specifically says that we will use loose tube, single mode fiber optics with low water, peak, gel-free installation. So we talked about the loose tube fiber optic cable type, and now you can see that that is a mandated requirement here within Florida Department of Transportation. Similarly, you can see down here highlighted in the middle where it talks about the diameter of the individual fibers. We are required to use a 1550 nanometer single mode fiber optic. Looking further into the specs, you can see here that the buffer tube contains 12 fibers, just like we talked about. That's the industry standard from TIA 598D. In the next highlighted section, talks about the TIA 598D standard and requiring that all installations on projects in the state of Florida shall utilize cables with the same industry standard color code. Now moving down to section 633-2.1.1.8, the outer jacket, you can see here that each cable is required to be stamped or printed with the words FDOT fiber optic cable. This allows us to quickly identify our assets in the field. And we just finished talking about this, but the minimum bending radius is also identified here in the spec. Here in the highlighted section of 633-2.1.1.9.2, it identifies that the minimum unloaded bending radius of the cable shall be 10 times the cable diameter, and then that the minimum loaded bend radius shall be 20 times the cable diameter when applied with pulling tension, which is exactly what we discussed previously. Keeping with the minimum bending radius, section 635, which is the pull box and splice vault section, also identifies that fiber optic cabling shall not be bent to a minimum bending radius less than 14 times the diameter of the cable when installed in boxes for long-time storage. And with that, we conclude our Fiber Optics 101 Basics in Cabling episode. Now remember, this is just the first in a multi-part series in which we will be walking through fiber optics. On deck for you, we've got Fiber Optics 102, Connections and Hardware, which will walk through fiber optic splicing, terminations, and all the associated hardware necessary for a full deployment. Following that, we will have Fiber Optics 103, which will walk us through the procedures and processes for the design, testing, and installation of fiber optic communications. Today, we went over 3 primary objectives. First, we wanted to understand how fiber optic technology works. How are we able to send pulses of light from the source to the destination in order to exchange loads of data from point A to point B? Second, we wanted to understand why the department employs fiber optic communications. What are some of those benefits? And remember, we talked about higher speeds, longer distance, greater bandwidth, better reliability, and more security. And finally, we wanted to learn what fiber optic cabling is used in typical construction projects. So we talked about the components of a fiber, whether that be the individual fiber itself with core, cladding, and coating, or how those individual fibers are rolled up into buffer tubes, and how each cable is constructed of multiple buffer tubes, multiple fibers, and also additional components like the central core member, the outer jacket, and everything in between. We also discussed the various types of fiber optic cables, from loose buffer tube to armored to aerial communications. Thank you for joining us for the Fiber Optics 101 Basics in Communication. As a reminder, this presentation is sponsored by the Florida Department of Transportation and presented by AtkinsRealis. If you have any questions or comments or would like further information, please refer to the email addresses in the video description. We look forward to you joining us on the future episodes of the Intelligent Transportation Systems Masterclass. Thank you.